Today, with real numbers in the number line, you're going to be able to classify, to graph, and to compare real numbers and find and estimate square roots. With square roots, this goes hand in hand with exponents. The whole expression is called the radical. The symbol, this box, it kind of has like a messed up check mark in front of it. This is called the radical symbol, and it tells the reader to take the square root of what's in the radicand, what is under the box. So it's an operation. It is the inverse of a square. Later on, you'll see things. It might be the third root, the fourth root, and those are the inverses of a cube or the fourth power of something. So the outside of it, the box, is called the radical symbol. The inside, what's inside the house, is called the radicand. This is the expression under the radical symbol. And I'm calling it an expression and not just a number because later in the year, don't get freaked out on me, but you might have something like 49y squared. With square roots, to simplify simply means to get rid of that radical. That radical symbol, remember, is like an operation sign. Square root of 900. Well, the 9 should look familiar to you because you know that 3 squared is 9. And then the 2 zeros, think of 100, and you know 10 squared is 100. You can kind of test this out. So we know there's a 3 and we're thinking of 10, so let's think 30. If I were to do 30 times 30, that would end up being 900, so that is equal to 30. For B, 1.96. What should be coming to your mind and looking back at your cheat sheet of common perfect squares, you know that 14 squared is equal to 196. So there's the digits. I just have to think about decimal placement. Think back to multiplying decimals. It's 2 spots over. So wouldn't that work if you had 1.4 times 1.4? That would be 196, and the decimal comes over 2 places. Therefore, simplified, that is equal to 1.4. Now, estimating square roots, that means to find the perfect square that is closest to what is in the radicand. So thinking about 17, the perfect squares that come to mind are 16 and 25. So the square root of this is going to be either square root of 4, it's either going to be 4 or 5, and it's clearly closer to 4 because 17 is really close to 16. So in my head, what I thought about was that 4 squared equaled 16 and 5 squared equaled 25. 17 falls closer to 16, therefore we're going to estimate that. I need to put a squiggle there because we're estimating 4. Coming over here to 242. Thinking about some perfect squares here. We know that 15 squared is 225. Let me see what 16 squared is. It is 256. So I have to decide which of these is 242 closest to. Well, 256 is 14 higher, and 225 is 17 less than it. So it's going to be closer to 16. So we're going to estimate that as 16. Here's some other work with real numbers. First, naming the subsets to which each number belongs. So think about that diagram that we created of rational numbers, of integers, of whole numbers, of natural numbers, to see which ones these belong to. So let's start with 2/3. The most basic number was a natural number, counting numbers, 1 through 10. It's not a natural number, nor is it a whole number because it's a portion of a number. If it's not a whole number, then it can't be an integer because an integer is a positive or negative whole number, but it is a rational number. It is a rational number because it obviously can be written as a fraction, and when we do the decimal of that, that's equal to 0.6 repeating, and the decimals either have to repeat or they have to terminate to be considered a rational number. Let's go to pi over here. Think of pi as a number, not as a variable. Pi is an irrational number. Here's why. If you were to push pi on your calculator, we think of pi as 3.14, but that's the rounded version of pi. So in the calculator, 3.141592654, it actually goes on and on and on. Beyond that, it's not going to repeat, it's not going to terminate. Therefore, it is an irrational number. That was the category of numbers. It was off all by itself. And on our last practice problem down here, order these numbers from least to greatest. We have all kinds of numbers down here. We're going to need to write them all in the same language to be able to compare them and think about them on a number line. I think it's easiest to think of these in terms of a decimal. So 1/2 would be like the decimal 0.5. -2, obviously, we can keep it as -2. The square root of 5, it's going to be 2 point something because I know the square root of 4 is 2. Let's put this in here. It is 2.23606, and it goes on. It's irrational. It's not going to terminate. Negative 7 over 4. Well, 4 goes into 7 once with 3 left over, so that'd be negative 1.75, and then we have 2.4. Now that I have them translated, I'm going to write them in the correct order from least to greatest, and as I'm writing them in the correct order, I'm putting them back into the original language that it was written in. The least number, we're going to go to the negatives and think about what's farthest to the left, which is negative 2. So I've used that one. I'm going to cross it out. Then I'm going to go to the next negative, negative 1.75, which was originally negative 7 over 4. Cross it out. Then I have 0.5, 2.2, and 2.4. 0.5 is less, so let's put that one up there. It was originally 1/2. Then I have 2.2 and so forth, which is going to be less than 2.4. That was square root of 5. And what's left was 2.4.